Hi, everyone. Welcome to the 2025 Systematic Review and Meta-Analysis Seminar Series. It's great to see a bunch of familiar names on the Zoom and also some folks I haven't had the chance to meet. So welcome. Today, I'm really pleased to introduce Dr. Man Chen. Man has a master's in quantitative methods from University of Texas at Austin, master's in statistics from UW, and also a PhD in quantitative methods from UW-Madison, where I had the pleasure of working with her for a number of years. Her work spans a number of different areas of meta-analysis, including synthesis of single case designs, and also work on sussing out the issue of selective reporting and publication bias in meta-analysis. And she's going to be sharing some of her work in that area today. So thank you all for coming. Thank you, Man, for joining us, and please take it away. Oh, actually,
Sure.
I should say usual ground rules. The presentation will be 40 to 45 minutes. If you have questions during that time, you're welcome to leave them in the chat, and we will monitor the chat and kind of collate the questions for the discussion period at the end. Sorry, go ahead, man.
Thanks. Let me share my screen. Am I sharing the right one? Yes. Okay. All right. Hi everyone. Happy Valentine's Day. Okay. So I'm very honored to be here today and present my work on adapting methods for correcting selective reporting bias in meta-analysis of dependent effect sizes. This is actually the first study in my dissertation that investigates the intersection between selective reporting bias correction method and also dependent effect sizes in meta-analysis. Let me start with some background and motivation for the study. So empirical evidence has suggested the existence of selective reporting at the study level and also the outcome reporting bias in different fields, such as in healthcare, in psychology, in education, and also in other social science fields. And then in a paper published on apes like a decade ago by John and his colleagues, they looked at the prevalence of questionable research practices. And then they surveyed over like 2,000 psychologists about their involvement in questionable research practices. And then they found that the percentage of respondents who have engaged in questionable research practices was surprisingly high. But how surprisingly high? So I grabbed some data from their findings. So all those numbers are based on the responses from the treatment group. So basically, the top on the list of this questionable research practices is that many, like 67% of those respondents reported or admitted that they failed to report all of a study's dependent measures. And then 58% admitted that they collected more data after seeing whether results were significant. And also some people reported that they selectively reporting studies that worked. And also there are some practices regarding deciding whether to exclude the data after looking at the impact of doing so on the results. So if we summarize all those practices, like the first one, you can think about this as selective reporting of the specific outcomes or dependent measures within your study. And then there is some p-hacking strategies or practices. And there's also like selective reporting of the whole studies compared to like particular outcomes. So basically, by definition, questionable research practices refer to a variety of problematic behaviors in research design, analysis, interpretation, and reporting stage that produce favorable results, but undermine the credibility and rigor of scientific research. To name a few of like common questionable research practices, The first one might be selective reporting of positive findings, which is the focus of my current study. There are some other common questionable research practices that have been investigated by many researchers, such as p-hacking or phishing for statistical significance, and also like hacking that represents hypothesizing after the results are known. Of course, there are like other types of questionable research practices. So like I said, I'll focus on the selective reporting of positive findings. So selective reporting occurs if affirmative results within a study or the entire study are preferentially reported based on some statistical properties. And those affirmative results might be those statistical significant results that are like positive. And those results are usually more likely to be included in meta-analysis compared to non-affirmative results that are not significant or that are negative, right? Selective reporting can result in overestimated average effect size, inflated type 1 error rates, and also inappropriate inferences about the intervention effects. So to illustrate the effect or impact of selective reporting on the average effect size estimate, I simulated some data here with like 500 studies in a meta-analysis. And the true effect is set at 0.6, and there's between study heterogeneity of 0.1. So basically, on the left plot here, we have the funnel plot of all the effect sizes without selection or before selection. And then if you look at this funnel plot, we can detect some results that are significant and non-significant. We have some positive effects and we have some negative effects. So there's no like clear pattern between standardized mean difference and standard errors. So there's no clear pattern for small study effects. And then if you run a random effects model, the average effect size estimate is about 0.6, which is close to the truth. But then if we apply a pretty severe selection here, that we only keep those effects that are significant and also positive. So on the left panel, we can see, okay, for those effects that we select, there seems to be a clear pattern going on between the standardized mean difference and the standard errors. Yes. And then it seems like studies with larger standard errors, meaning like smaller studies, tend to report large effect sizes. And then if you run a random effects model and the average effect size estimate will be estimated as like 0.8, where we have a really severe overestimation. To handle those selective reporting or like to deal with the selection bias caused by all those different selective reporting strategies, there are like various existing methods for doing so. I'm listing just some of the methods because they are kind of like relevant to my study here. So first method is regression-based adjustment methods for small study effects. And then we have a couple of methods proposed by Stanley and his colleagues. You might be familiar with pattern Ps, and there are also like recently developed methods, including weighted average for the adequately power, and then weighted and iterated least squares estimators. There's another method that's based on piecewise regression model proposed by Baum and Rechinger. That's called endogenous kink meta regression model. All those methods are kind of like based on the relationship or like try to model the relationship between standardized mean difference and effect sizes and try to find a way to correct for bias caused by selective reporting. There's another class of really popular methods called selection models. The first one that I'm listing here is the p-value selection models, which are commonly used in practice and also in simulation study. I'm gonna use this p-value selection model in my data generation process in the simulation study. And there are some other methods developed based on the distributions of the p-values, such as the p-curve and p-uniform and p-uniform star. We included like the p-uniform and the p-uniform stars in the estimation of the simulation method. That's why it's they're here. Okay. So basically, I'm gonna spend like a few minutes reviewing these methods because, like I said, it's relevant for my study. And also, like, I'm gonna adapt some of the methods with a new weighting scheme. Okay, so to start with some univariate regression-based methods, this plot is still for the simulated data of like 500 studies, and the true effect is 0.6 as indicated by this dotted horizontal line here. And this plot is kind of like the rotation of the funnel plot that you just saw when there is selection, right? So it seems like there is this upward trend going on between the standard error and the effect sizes. For the method like PET, which is called a precision effect test, the method actually tried to model the relationship between standardized mean difference effect sizes and standard errors using a linear function. That's actually the blue line here, blue dash line here. And then the average effect size estimate is around 0.5, indicating there's like some underestimation going on when the true effect is greater than 0. And then another method, precision effect estimator with standard error, that's PEAS, tries to model the relationship between effect size and standard error using a quadratic form. And then the estimate for the average effect is 0.569. There's some improvement in the average effect size estimate, but there's still some underestimation going on. And lastly, we have EK model here that use this nonlinear or like this piecewise regression that try to capture this relationship. And then basically the idea is that there's some cutoff on the standard error. So basically for effect sizes that are under this cutoff here, those effect sizes are less likely to be subject to selective reporting. And then for effect sizes above this cutoff, with standard errors above this cutoff, the model tries to model this relationship using a linear form. And then in this scenario, the EK estimate is pretty close to PEAS. So basically, for all these three methods, they're trying to kind of like adjust for this small study effects based on this regression with like different forms. And then for the other two regression methods that we looked at, the first one is WAP. This estimator is actually trying to keep or just discard some of the studies with really less power and only keep the studies or look at the studies with sufficient power. And then they estimate effect sizes or run the meta-analysis model based on those effect sizes from the studies with sufficient power. And in this scenario, all those like gray dots or like studies are discarded. And then the average effect size is estimated as like 0.61, which is close to the truth, but there's like a really, really slight, tiny overestimation for this scenario. And then lastly, there is this method called weighted and iterated least squares. It's called WILS. It's an iterative process that actually remove or discard large effect sizes step by step or iteration by iteration. So basically, in the first iteration, if you run this algorithm, the average effect size estimate is about 0.6. There's like overestimation. And then with more iteration, we're removing more large effect sizes on the top right corner. And then, so basically after 5 iteration, we will end up with an estimate of the average effect of like 0.45. If you keep going, of course, there's like a stop rule. And then, and if you keep going, I think basically you'll end up with like less studies and less effect sizes. And then there might be an estimation with this level of like, removing the effect sizes. So all these are the regression-based methods, and I'll talk about how to adapt those methods to the multivariate case shortly. Another class of method, which is selection model that actually try to model the selection process or selection mechanism with the selection model or like a probability function. So if we look at the 3PSM model here, we have a random effects model for the data model. And then for the selection process, we are using this step function that actually indicates that for effects with p-value less than 0.025, the probability of observing this effect is 1. And then the relative probability of observing effect size with p-value greater than 0.025 is lambda. And lambda is actually less than 1. So with this data model and this assumed selection model, we would be able to derive the observed or like the density of the observed effect sizes. And then after that, we can apply some estimation methods to estimate those parameters. And then the estimated like mu, which is the average effect size, would be the estimate that after you account for the selection process. Okay. Although we have all those like different regression-based methods and also a bunch of different selection models and other methods that are like closely related to selection models, many of these methods are based on this assumption that the effect sizes are independent. So basically, because it's kind of like most of the methods were proposed really early for like univariate meta-analysis, where each study only reports like one effect size. So basically, you can be confident that all those effect sizes are independent. However, in practice, in like education, in psychology, and other fields, in social sciences, meta-analysis, we often have this dependent effect sizes, maybe because we have multiple outcomes, multiple dependent measures within a primary study. And then we actually have many methods developed for handling dependent effect sizes, such as multi-level model, multivariate methods, and robust variance estimation. However, there's still a lack of methodological development on the intersection between selective reporting methods handling detection or adjustment methods for selective reporting and the handling of dependent effect sizes. So that's basically like the motivation for my study. So the purpose of the study is firstly to propose a new weighting scheme for the correlated and hierarchical effects model in RVE framework to account for effect size dependencies. And secondly, the goal is to adapt univariate regression-based adjustment methods using the proposed working model and weighting scheme. And lastly, we want to evaluate the performance of these adjustment methods, including those novel adaptations in a simulation study, assuming a p-value selection, like p-value selection forms, because p-value selection form is kind of like a popular and pretty simple, but also common selection model or form. All right, now let's talk about Che-Iskew and novel adaptations. We tried so hard with this acronym so that it sounds like it's, proposed by someone from Pustyovsky's lab. The motivation for this Ch-isQ weighting scheme in the multivariate case is that in univariate meta-analysis, fixed effects model weights were proposed to be used in random effects meta-regression models so that we can relatively allocate more weights to large studies that are less likely to suffer from selective reporting. So based on this univariate method, we propose that, okay, we could do similar thing in the multivariate scenario. So there are like three parts with Ch-isQ. The first part is the Chen model proposed by James and Beth Tipton. Basically, this model handles the dependency because it models it accounts for the nesting structure where we have effects nested within studies, and then it captures the between study and within study heterogeneity, and also the correlation between the effect size, the error terms or effect size as the sampling process. And then the weights for a Chen model here is actually a function of, for a particular study, J, the weight is a function of the sample size of the study and also like the between study heterogeneity, within study heterogeneity, omega square hat here, and also the correlation among the outcomes within a study. And then, so the second part of this Ch-isQ model concerns the weights. So basically, instead of using this marginal variance covariance matrix weights, we're using this inverse sampling covariance weights. Basically, we try to just focus on the sampling covariance weights part. So basically, we remove, kind of like ignore the between study heterogeneity part and within study heterogeneity part in this original weight in the Chen model. And we will end up with this relatively simple weighting matrices here for each study. And then if you compare those two weights, if you think about, okay, if I have a pretty large study, so NJ is pretty large, and then if you have a relatively some level of between study heterogeneity, it will affect the denominator here in the Chen model. And then if you compare those two weights, basically Ch-isQ weights or isQ weights will allocate more weights to studies, to large studies compared to the original Chen model weights. Okay. And then after that, the third part is applying this cluster robust standard error for any misclassification of the model. So our novel adaptations actually is just applying this Ch-isQ working model and weight to those univariate regression-based methods. And hopefully, because by allocating more weights to large studies compared to the Chen model weights, hopefully we could find less biased average effect size estimates. And also we would be able to account for the dependency using that Chen model. So this is basically the focus or the method that we proposed in the work. Now let's talk about the simulation study. Okay, so there are a bunch of research questions regarding this Ch-isQ working model and all those adaptations. The first one is, how do the univariate adjustment methods perform in the context of dependent effect sizes in the presence of one-step or two-step selection? So one-step and two-step selection actually differs in how you model the selection process based on the p-values. So one-step is pretty strict in that, all the effect sizes that are significant and in the positive direction, they will be observed like 100%. And then for the effect sizes that are not significant, then there's like a less probability of observing those effects. But with two-step selection, we actually also like kind of like extend that selection model a little bit by allocating different ways to effects that are like positive versus negative. So it's a little bit more extension on one-step selection. We want to do this, or like we want to analyze or investigate the performance of those methods in both one-step and two-step selection, because we want to see how the results might change if we just tweak the selection process a little bit. And then the second research question is, in the dependent effect size context and under one or two-step selection, how do the adapted estimators based on JSQ perform compared to their univariate counterparts? And then lastly, we want to know, how do promising multivariate adaptive adjustment methods perform compared to the most effective univariate estimators? With all those research questions in mind, we designed this simulation study. For the data generation process, firstly, we generated meta-analytical data set with dependent effect sizes, and then we censored those generated meta-analysis data sets or effect sizes under a one-step and two-step p-value selection, so that we will end up with effects that, or like a meta-analysis that is affected by a different selection process or mechanism. And then we look at a bunch of estimators. I think it's around more than 20, it's a lot. Basically, we look at the univariate regression methods to see whether it's how necessary we need to consider dependent context. And also, we look at all those multivariate adaptations so that we can kind of like try to see how these adaptations work. For the performance criteria, we are particularly interested in the recovery of the average effect size estimate. We look at the bias, accuracy, and the confidence interval coverage and width. All right. So now let's talk about some key findings from the simulation study. So the first highlight here is that we should never ignore dependence. This plot is based on the results under one-step selection, where the number of studies in the meta-analysis is about 30, which is pretty small, relatively small. And then the average effect size is 0.2, and the average outcome correlation is about 0.4. In this one-step selection, if you look at the bias in the first row here, we have some estimators that seem to be pretty effective or like nearly unbiased for different between study heterogeneity of 0.1 or 0.4. That estimator is 3 PSM, which is kind of like expected because the underlying selection process is one-step selection. And then for some other estimators such as EK and PET-MPs, there is some level of overestimation for small between study heterogeneity, and then it's just getting worse for large between study heterogeneity and for severe selection. And then we have the Webb and Wills, they just tend to be more positively biased for severe selection and for large between study heterogeneity. And then interestingly, we have some underestimation going on with Wills. So this is for bias. And then overall for the accuracy, basically 3 PSM tends to be more accurate compared to other estimators across the different level of selection, and also for different between study heterogeneity. And lastly, for the coverage, remember that these methods, they're like based on they're univariate methods, so they just ignore the dependency among the effect sizes. So for 3PSM, although it tends to be nearly unbiased and it's really accurate, more accurate than all the other estimators, it tends to undercover the true effect because it ignores the dependency among effect sizes. And then for all the other methods, I mean, it's a mess here. We for like strong selection, all these other estimators based on regression models are like it's really bad for the coverage. So this is like what happens when we ignore dependency just using the univariate estimators. Next, this is regarding the second research question about how the Ch-isQ-based multivariate adaptations work compared to their univariate counterparts. So here on the x-axis, we have the performance or like the bias. This is the first place, the bias of the univariate estimators and then the bias of the multivariate estimators after the Ch-isQ adaptation. And then basically here, I guess the takeaway is that generally speaking, Ch-isQ-based multivariate adaptations are less biased than their univariate counterparts across all these conditions, like different between study heterogeneity or for different true effect size for if you have like 30 studies. And then this pattern also holds if you have more or like a larger meta-analysis. And then the result here is based on one-step selection, but it generally holds for two-step selection as well. The next one, we have the accuracy here for the Ch-isQ multivariate adaptation methods or estimators, and then the original univariate estimators. Still, we kind of like, we are able to see, okay, for most of the adaptations here, for example, for the EK or PenMPs, and even for web, the univariate methods tend to be less accurate compared to the multivariate adaptations. Whales is like unique here. There's something going on with whales because if you think about the end estimation with the effect sizes and also the problem with the accuracy and also the coverage. But still we can see, okay, for most of the case, multivariate adaptations tend to be or closely to be like more accurate than the univariate estimators across different like level of selection. All right. Lastly, we compared the 3PSM and 4PSM because those methods of at least they are like less like nearly unbiased or they are more accurate than other univariate methods. Although there's like some problem with the confidence interval coverage and width. So we kind of like grabbed 3PSM and 4PSM here. And then we have this multivariate EK and PETs here because they seem to be more promising, or at least they perform better compared to other methods in different scenarios. And then we have Ch-isQ as kind of like a baseline estimator here. We compared those estimators. Some of those are based on multiple variate adaptations. And then some are like just original univariate estimators, like 3PSM and 4PSM. So basically the takeaway here is, unfortunately, there's no clear winner here. There's no one method that outperforms all the other estimators in different scenarios or across different simulation conditions. So under the scenario where we have this one-step selection, and if the average effect size is 0.2, if the average outcome correlation is about 0.4 for a relatively small meta-analysis, we can see that it's the same story with 3 PSM and even with 4 PSM. They're less biased than other methods. They're nearly unbiased. They're more accurate for some conditions compared to other methods. Although they suffer from this undercover for the cover for the true effect. And then for other methods like JSQ, because JSQ is just relying on this idea that, okay, we tried to allocate more weights to large studies. So hopefully they can be more robust to selection bias. And it is, if you compare to the univariate case, if you compare to JSQ to Che, we can see the effect of like the tweaking the weights. However, compared to other regression methods that actually for the adjust for the selection bias, JSQ is kind of like performing the worst here for some scenario compared to other estimators. So it tend to be JSQ tends to be more biased than other estimators. And then it's interesting that if the selection is really weak or if there's no selection, then JSQ is just good. It's like nearly unbiased. It's really like accurate, and then the coverage is good. But then with more severe or moderate selection, it's not working well. And then multivariate EK and pattern piece, they're kind of like in between. If you compare to JSQ and also selection models. So there's some scenario that they seem to be okay, but then overall they just kind of like tend to fail to they tend to fail for strong selection. Okay, so the implications here is that firstly, at least based on the first highlight of the results, meta-analysts should not ignore effect size dependencies when correcting for selective reporting bias. However, because none of the methods, at least the methods that were included in this current study, none of these methods performs adequately across all the simulation conditions. So sensitivity analysis are recommended in practice if you need to handle both selective reporting and also effect size dependencies. And then while methodological work is yet needed for further developing more robust adjustment methods for selection bias, the most efficient strategy for addressing selective reporting is to prevent its occurrence. So basically, there's still a need, there's a need for more methodological work in this context for handling selective reporting in the context of dependent effect sizes. Why we're doing that, like the best way to handle if selective reporting is like prevent it from happening. So, we still suggest researchers or meta-analysts pre-register their studies and then try to report all the outcomes or all the results or findings, no matter it's positive or negative, so that it's just good for meta-analysis and also for generally for evidence-based practices in general. All right, so there are some limitations and future directions for our current study. The first limitation here is that the simulation here in this study is limited to one or and two-step p-value selection of the outcomes within study. But then, as we have seen in the paper by John and his colleagues, there are even for selective reporting, it can happen at within study level when we selectively report some outcomes or specific outcomes. But also it can happen at the study level. Although some primary studies have multiple outcomes, and then no matter what is the status or like the statistical properties of those outcomes, the selection might happen at the study level. So there's something that might determine whether the whole study of including all those outcomes will be published or suppressed. So future research should consider other types of selection mechanisms. Or the other way to put this is like, our findings are just specific to those or limited to those specific selection mechanisms that we are investigating. It's going to be interesting to see how those methods work in other potential selection mechanisms. So secondly, the JSQ working model only includes the unexplained heterogeneity. So we didn't consider covariates that might help with explaining or reduce selection bias. So future research could consider incorporating moderators to explain the heterogeneity. Lastly, the current study only examined the recovery of average effect size parameter. So we're only looking at what is the overall average effect size. Research is still needed to evaluate heterogeneity estimators in the presence of selective reporting and effect size dependencies. There's some work in the univariate meta-analysis looking at how selection or like problematic practices might affect the estimation of the heterogeneity in the effects in the meta-analysis, but that's like in the univariate case. So there's still some room for the work in the multivariate context. All right. So these are like just some limitations and potential future directions that I can think about. And like I said, this study is like the first study in my dissertation, and actually I'm continuing working on this problem, and I'm trying to kind of like propose some other selection mechanisms and try to check how these methods work in different selection mechanisms. So thank you for your attention. I put the preprint link here down here. So if you're interested to learn more about the work and also about some other results, because I only kind of like presented part of the results and for some of the estimators, but if you want to have to see what's happening with all those estimators across all those conditions, under one-step selection or two-step selection, please feel free to check all those information in the preprint. Thank you so much for your attention.
Thanks, man. And we've got a good amount of time for questions. I see Betsy posted a question in the chat. Betsy, would you like to pose it again? Or I'll just read it out. So Betsy asks, I'm wondering why you chose to use the like rho sigma j squared, so as a covariance between the sampling errors, rather than using a known covariance formula for the effect sizes.
Thanks, James. That my mouse malfunctioned for a while, so that's the actual question.
Yeah, anything to add?
Slide 22. No, I mean, I'm just curious. Obviously, it's easier. You've got the variance already, and this might be kind of a general all-purpose approach. It's obviously going to be a little bit different from the actual covariance, although both of them depend on rho. So I'm wondering, do you have any sense of how close this is to, and I'm, you know, every variance and every covariance is different. So
That's right.
I get that. But
Yes.
is there any benefit beyond that?
Yeah, I guess the quick answer for that is like it's kind of like you said, it's easier to assume a equal uh, variance for those multiple effects within a study. And then I guess it makes sense in a way that because we're looking at multiple outcomes within a study based on the same sample. So it makes sense to make this kind of assumption, but I definitely agree that we could um, extend this just a little bit to allow for the difference in the sampling variances. Um, but considering like the scenario with multiple outcomes, um, or based on the dependent effect size measures themselves, we might see a little bit more discrepancies or differences in the sampling variances. But then generally, I think this is a assumption that people make in practice for some of the work they do. Yeah, I hope that um, answers the questions. But I really appreciate your question or insight into this equal sampling variance assumption.
Yeah, I mean, I think the times that it might be problematic would be, at least for delta and D type effect sizes, would be when you have one result that's somewhat deviant, because that usually makes the variance bigger. And so assuming that the variances are equal to each other means you're going to give that effect size more precision than it deserves, and take away the precision from the one that's not quite so out there.
Mm-hmm.
And I mean, when you're worrying about things that are, reporting bias, I mean, I always worry about things that go in both directions. And so, yeah, that's the only thing I could think of. I know there's a number of cases where actually the correlation between effects based on the fancy covariance formula, and dividing by the roots of the two variances, actually turn out to be really close to rho anyway. So it ends up, in several cases that I've seen, that is a pretty close approximation. But yeah, that's the only case I could think of that would worry me, because on occasion you do get, people using things. Maybe they're less dependent in a case like that as well, where the effect sizes are wildly different from each other. So it could be a thought to, have some sort of rule where if the effects are divergent in some way, I don't know how you'd make the judgment about it, but to maybe use a lower value of rho than you're using across the board, and to not use the mean of the two standard deviations, or the mean of the variances. But I mean, it's an empirical question. You could play with it and see what happens. So
Sure, of course. Yeah.
yeah.
Yeah, I
Anyway,
guess
nice,
like
yeah, nice talk though. Very nice
thank you,
talk.
thank you so much. I guess like the focus, at least for this current study, is like we're looking at how we can allocate different weights to studies with different sample sizes. So basically, what's happening within the study is kind of like at least in this stage is not like fully investigated, but I truly appreciate the suggestion that maybe for within study for each effect sizes, we could consider how their sampling variance might affect the weights that we allocate to them. So it could be a nice further extension or direction to look into.
Yeah,
Thanks for that.
could be a quick side study.
Yes.
Anyway, thank you for your nice answer.
Thank you.
Other questions? Feel free to raise your hand down at the bottom of the Zoom, or post questions in the chat as you like. Question from Noah.
All right, so I'm going to be that guy who's going to ask a low-level question in a room full of statisticians because it's fun. So I'm one of those people who needs to take a while to read a paper and stare at stats before it sinks in, right? And look at graphs. And I like to know the end purpose as I'm staring at these things, just because it helps things click in my brain. So my takeaway from your presentation, I want to make sure it's right before I read the preprint, is that when we're dealing with the dependent effect sizes, none of these methods that were tested work perfectly in every scenario. And our takeaway is still we need to be doing sensitivity analyses. I just want to make sure I'm on the right.
That's right.
Before I
That's
dig into the math.
totally right. Correct. Yes.
Yay. Okay. Well,
Unfortunately, yes.
Well, no, I mean it's unfortunate. You say unfortunate, but I don't think it's really unfortunate. I mean, I think that's kind of the fun thing about stats, personally, is like when we find things that don't work perfectly, I think that's still good to know.
Yes.
But I just wanted to say thank you because you presented a lot of math here, and like I said, I'm one of those people I really need to stare at papers a while before I get it, and I apparently got the right takeaway point from your presentation, so that's very good. That doesn't always happen. So thank you again for that.
Thank you. Sure.
Just kind of following on Noah's question, one thing that folks may be wondering is like if they want to kick the tires on these different adaptations, do you have any sort of suggestions on how they could implement them?
I wish I finished the tutorial paper. We have a tutorial paper on this, but because I am still as a first year faculty here, I'm struggling with my classes, of course, and I'm also struggling with my research. I'm working on like the second study in the dissertation with all those various like different selection mechanisms that we're proposing. And then we do have a tutorial paper on like how you could use some of those promising multivariate adaptations such as multivariate patipes, EK, and also the selection methods like 3PSM, and also how we could also incorporate the sensitivity analysis proposed by Dr. Maja Murther, that we can kind of like run these methods and try to compare all those average effect size estimated across those different methods and across the different assumptions on the severity of the suppressing or censoring. I hope I can finish. I can finish that soon. But yeah, we do have some at least in my dissertation, if you're interested or like curious about how you could apply all those methods, how you could incorporate the sensitivity analysis in your analysis and compare all those methods, you could feel free to check I think the third study in my dissertation. It has some like code and also some explanation or like interpretation, how you would interpret the results if you have found, or if the results kind of like are not consistent across different methods. Yeah.
Harry,
do you have a question?
Yeah, I do. So, I mean, I'm going to maybe follow along with Noah, but
Sure.
but I actually wanted to understand because this is a really active area, all this work on thinking about selection models. I'm wondering if, I know Mega and James are working on other methods. So could
Yes.
you just sort of kind of put this in put what they're
Yes.
doing in
Yes.
your context too?
Yeah,
That would
yeah,
help
yeah.
me. Yeah, thanks.
Yes. So basically what we have observed in this study is that I didn't do anything with the selection model like the 3PSM or the 4PSM model. It's just the original model or method. And then I know James and his colleagues at AIR has recently worked on handling like the undercover confidence interval, like the problem with the standard errors using bootstrapping, and then seems that this the p-value based selection model like the 3PSM and other methods, 3PSM for example, works well after using like the bootstrapping methods. So basically the confidence interval seems to be the coverage of the confidence interval seems to be within the accepted range. And then considering that, it seems like those selection models will perform pretty well in the dependent context for handling selection bias or publication bias. And then their methods are also similar to what we are doing here with the selection process, are kind of like a specific or concluded based on those one step or like two-step selection. I can't remember which selection mechanism they're looking at, but it's based on p-value selection. And then, but if we consider all the other potential selection mechanisms, or like the selection mechanisms themselves could be really complex in reality. If we consider that, maybe the next step would be like, try to examine or investigate the methods here with the the multivariate adaptations, especially considering the covariates that might help with improving those methods, and also with James' work on and Mega's work on the selection model in different selection or under different assumption of the selection process, how those methods could work with another selection scenario. I think that would be an interesting thing, or like an important next step for all this work. Yeah, that's I hope I answered the question.
Yes, you did. Thank you. No, that
Thank you.
helps. I
Thank
think
you.
we have maybe time for one more question. Does anyone have a question? Okay, well, I just want to, James had to step off early. If you don't know who I am, I'm Terry Piggott. And I just want to thank you all for being here. I want to remind you that we have another one coming up on March 14th, which is about living systematic reviews in social emotional learning programs. So hope we see you then, and thanks again for coming.